This video is part of a series on the xv6 operating system kernel. In this image, we're executing in the user code. We get a trap and we execute something in the kernel, and then we execute a system return instruction and go back to user mode. In this video, I'm going to talk about what happens when we're in kernel mode. I'll talk about the data structures in particular, and I'll do a code walkthrough of the proc.h file. So let's begin with this thing that I call the roadmap, and it shows everything that happens between the trap and the sret instruction. And let's go through this more carefully here. The trap could be caused as a result of an asynchronous interrupt. Either the timer is requiring attention or an I/O device is requiring attention. Or it could be a synchronous exception due to a system call by the user mode code or some sort of a program error. The hardware will do several things. It will disable interrupts, it will switch to supervisor mode, it will save the program counter in SEPC, it will save some information about what exactly caused the trap in this scause register, and it will load the PC with the address of the user-vec function. There is a control and status register called stvec, and that contains the address of the code that's supposed to handle any kind of a trap. And so that's how we branch to this assembly code that is located in the trampoline page. So this trampoline page, recall, is mapped into all address spaces, both the user address space and the kernel's address space. And it does the initial saving of the user's state. So what does it do in particular? Well, it saves all the general purpose registers and the program counter in the TrapFrame. Each process has its own unique TrapFrame, but they're mapped into the second highest page in the user's address space. This code is executed in the user's address space. So then we get ready to start executing kernel code, and every thread needs its own stack, so we have to initialize the stack pointer register, and we also initialize the TP register, which contains the core number. These two registers will have other values in the user code. We can't trust what values they might have had, so we need to load those, but we don't really need to load anything else. We then load the SATP control and status register with the pointer to the kernel's page table. So that will switch us effectively into the kernel's virtual address space. And at that point, we then jump into this function called user trap. And this is C code. And what does it do? Well, it's got an if statement, and it figures out what exactly is going on. But first, it stores a pointer to another trap vector in stvec. Previously, stvec contained a pointer to this function here, but if a trap occurs while we're executing in kernel mode, we want to handle it a different way. So we update stvec here. And then we look at the cause register, the scause register, and determine whether it was some sort of a program exception. If there's an error, we print a message and call a function exit, which will terminate this process altogether. If a device needs handling, well, we call this device interrupt function here to take care of that. There's a Boolean called killed that's associated with each process. And if it gets set, we need to terminate that process. So if for some reason this process has been killed, somebody else wanted this process to die, well, they would have set that Boolean to true. And at this point, we check it. And if it's the case that this process should die, after handling the device interrupt, we then call exit. But probably we just continue down here. If the timer interrupted, then it's time to have the end of this time slice and give some other processes a chance to run. So we check the killed thing, and if so, we just exit. But otherwise, we call yield. Yield will eventually return, but what it will do is it will cause the execution or allow the execution of other processes. It will invoke the scheduler, and some other processes, which I've hinted at here, will execute, but eventually we'll get another time slice and return to yield, and then yield will return, and then we'll continue and go back into the user mode process. If the cause of the interrupt was, or cause of the trap was a system call, then we enable the interrupts. Okay, so this thread itself may be interrupted. For example, there could be a device requiring attention while we're dealing with this system call. Interrupts are enabled, and so that might actually occur. We might go off and do some other stuff. But in any case, we handle the system call, and then we come back, and at that point, somebody has asked for this process to die, then we call exit, but otherwise we continue. And then finally, whatever the case is, we call a C function, user trap ret, or user trap return, and it will begin the process of returning to the user mode code. It will disable the interrupts in case they got enabled here, and it will set STVec to point to uservec. So now this is in preparation for the next trap, so we need to have it point to uservec. Then we need to save into our TrapFrame values for the stack pointer, and we need to save the core number that we're executing on. Remember, we loaded these here. Well, here we're setting them up and getting them ready to go for when the next trap occurs. The SRET instruction will rely on the SEPC register, so we retrieve the saved program counter, and we put it into the SEPC register. And then we jump into some assembly code, and this assembly code is located in the trampoline page. It's called userret, and this will complete the process and execute the SRET instruction. It will, now that we're executing in the trampoline page, we are in that top page that lives in every address space, and so we can switch from the kernel's address space to the user's address space, and we do that by loading the SATP register with a pointer to the user's page table. And then finally, we restore the user's registers, and we also set a couple of bits in the status register. The SRET instruction will use the status register, and we set bits to tell the SRET instruction we want to go into user mode. We want the previous privilege level will be user mode, so we will be returning to user mode, and the previous interrupts enabled flag we set to enabled, so this will be copied into the current interrupts enabled flag. So when we execute the SRET, interrupts will then become enabled, and we will be in user mode, running with the user's registers and the user's page table and so on. Okay, so let's now take a look at some of the data structures that are involved. First of all, let's take a look at this TrapFrame. While we're executing in user mode, there's a control and status register called scratch, and it will point to this TrapFrame, and that will be useful. This contains the place where we will save the user mode registers. So up here, when we save the registers in the PC in the TrapFrame, that's going to happen, and that information will be saved here. The 31 general purpose registers will be saved here, remembering that the 32nd register, that is register 0, is always hardwired to 0, so we only have to save 31 of them. And the program counter, the previous program counter, will be saved here. So that's the state of the user mode thread. And then we load up the state for the kernel thread. So we have a pointer to the kernel's page table. That's nice and handy to have, and that's right there. We have a pointer to the stack that this particular process will be using. And then we have the address of user trap. That's actually not really part of the state of the supervisor thread, but we have that in this TrapFrame as well. And finally, we have the heart ID, or the core number, if you will, which we will need to load into the TP register when the trap occurs. So that's what's going on the TrapFrame. We have some other crucial and important data structures. We have a data structure called CPU. There is an array called CPUs, and there are 8 of these, 1 per core, and each one of these elements in this array is a structure, and that structure contains these fields. If a user mode process is running on that core, then we will have a pointer to the proc structure that describes it. Okay, if nothing is running on that CPU, or I should say if the scheduler thread is running, this proc field will be 0 or null. And I talked earlier about interrupts and how we can sort of stack them. We remember whether initially they were enabled or not. And then if we want to disable them, then we remember the initial value and increment a counter. And then when we back off, we can decrement the counter and ultimately return to the original state of the interrupts enabled bit. And finally, we have another register save area called context. Now, one thing I didn't really make clear was that when we're executing a process, we're executing either in user mode or in kernel mode. But we may switch, and I don't show this here, but we may switch over to the supervisor thread. Okay, and we leave that process behind. So we're really, in all of this that we're talking about here, we are executing as part of a process, okay? But in here, perhaps in here or in the yield, we will maybe go into another process's time slice. So we will have other context switches that are different. A context switch occurring here is different than a context switch occurring here. And so if we leave this process and go into the scheduler thread, we will need to save the registers. And so that's what this register save area is all about here. So let me point out, we don't need to save all of the registers. We only need to save some of the registers. And we'll talk about that later. If we are executing, if this core is executing a processes thread, then we'll have a pointer to a structure that describes that process. And it's got a number of fields, so let me go through these quickly. We've got a lock field. We have the current state of the process. It could be unused, used. It could be sleeping. It could be runnable, which means it's ready to go, and it could be scheduled, but it's just waiting for a time slice. It could be actually running, or after the process terminates, we call exit, it becomes a zombie for a little while before the structure is then recycled and becomes unused. If we are waiting on some lock, if this thread is sleeping, if it has the status of sleeping, then this channel describes exactly what it is we're waiting on. Here's that killed Boolean that I mentioned. After the process terminates, it has an exit status, and that's what this field is. And every process has an ID number, that's sequentially given ID number. This lock protects these fields. So let me zoom in a bit. This spin lock will protect these fields. In other words, if any of these fields are going to be modified or accessed, we need to grab the spin lock. We also have a pointer to our parent. So this is a pointer to one of these other proc structures. There are up to 64 processes. Well, there are 64 processes. Some of them may be unused, but we could have up to 64 processes running and runnable at once. And for each one of them, there is a structure. And this is the structure. And so this, I'm showing just the structure for one process. And parent points to whichever structure is the parent process, represents the parent process for this process. There is a stack for the kernel aspect of this process. So when we are executing here, okay, we need to have a stack for the kernel to use. Each of the 64 processes needs a separate stack. So that's given here by this. There's a pointer to that stack here. This is the size of the virtual address space, and here's a pointer to the page table for the user's address space. And then we have a pointer to our TrapFrame page. Each process has a unique page in physical memory, and so this points to that page. It will be mapped in. They will all be mapped into the second highest page in the address spaces, but this is a pointer to the physical page. And then we have another one of these context things. So this is another save area. So when we're switching back and forth between the scheduler thread and the process, we can use these two save areas. And we have an array here for open files and the current working directory. We even have a space for the name of this process, so we can give processes names. Okay, now that we've seen pictures of those, let's go ahead and look at the definitions in this file proc.h. So this is a context that was used both here and here, and you can see it contains the RA, that's the return address register, and that tells, that's the PC, if you will, where we go back to, and then the stack pointer. And then we only need to worry about the S registers. There are 12 S registers, and we only need to worry about those, so we only need to have an area to save those. Next, let's look at the CPU structure, this CPU structure here, and we see that it contains a pointer to the process if it's running, or null if not. And we have an area for the context, the save area that I showed here. And then we have these two fields that are the depth of the push off. Every time we call push off, it increments that counter. And this remembers whether interrupts were enabled before the initial push off. And then here we have our array of, well, we have 8 CPUs, so it's an array of 8 elements of these structures. The next thing we want to look at is the TrapFrame. So I'm not going to read through this information here, but here's what's going on in the TrapFrame. We're going to be accessing this in assembly code, so we actually care about these offsets. The TrapFrame is a page, and this will be page aligned, and these are the offsets given in comments here of each of these fields. You can see that each of these fields is a 64-bit number, right? And here are the fields that I mentioned. Let me get my TrapFrame picture here, and so you can we can go along. We've got the SATP, the stack pointer, this trap. I did these in a slightly different order. The saved PC, and then the core number. And then we have, you can count them, we have all 31 registers here. Okay, so we have all 31 registers there. Just in case you're curious, they're listed in sort of a strange order. For example, we have some T's here, we have some S's here, we have some A's here, we have more S's, and we have more T's down here. That's the actual way they're organized in the Risc-V processor, but we just care about, we just access them by name, and we don't really care which, this is register X1, X2, X3, and so on. So next, let's take a look at the proc structure. Okay, so that's this structure here. We're going to look at this structure here, and it's shown, whoops, let's see if I can zoom in there. The state down here is a proc state, and as I said, here are the states: unused, used, sleeping, runnable, running, and zombie. So when the process is actually running on the core, it has a status of, or a state, if you will, of running. When it's ready to run, and but unfortunately there's not an available core for it, it's just sitting around waiting for a time slice, it's runnable. If it has waited on something, it will go into a state of sleeping, and if it's terminated, it will become a zombie until it can be recycled. These structures are recycled. We only have 64 of them, so we need to reuse them after that process is killed. We need to reuse that structure. It remains in the zombie state for a little while until the exit status, this exit state, can be retrieved by the parent or whoever waits on it. And then at that point, it can be recycled and it becomes unused. And then used is sort of intermediate between unused and something else. So here we have the lock. That's very important. We need to lock the process. And in particular, we need to lock it whenever we're going to be using these fields. Here's our state field listed up above. Then we have this channel field. It could be 0, but I mean it's only relevant when we're asleep, and it tells what we're sleeping on. We'll get into how that works later, but basically it's just an identifier, and that identifies the different things that we might be waiting on. And here's the Boolean that indicates whether someone has asked for this process to be terminated. Here is an integer that is used to transfer an exit status from the process itself to whoever waits on it. And then this is an integer that's just the process ID number. Here is a pointer to another proc structure, that is the parent's process. Wait lock must be held when dealing with this field. And then we have some so-called private fields. The lock does not need to be held when we are dealing with these. This is the address of the kernel stack. Here is the size of the virtual address space. Here is a pointer to the page table that describes the virtual address space. Here is a pointer to the data page that the trampoline is going to use. This will get mapped into the second highest page, but here's a pointer to that. Here is the context area, so when we switch this process, we'll be using that. And finally, an array that is used for open files. Number of files is the number of files that can be opened simultaneously. And current working directory. And then we have a field of 16 bytes for a process name that we can use. Okay, I think that covers our roadmap, and hopefully this image will help you understand what's going on. In the next video, I plan to discuss the uservec and usertrap functions, as well as user trapret and userret. See you in the next video.